And then one is going to talk about phase field modeling.
Yeah. Yeah. Okay. So this is in continuation with what we are talking about. So mainly I will I will start with the molecular dynamics of polycrystals, but eventually the topic for today is some analysis on the grains that we get, in particular grain size distribution function, which I'll come to later. But first let me tell that we got polycrystals with MD also. It was actually we are forced to do this sort of because the claims that we made for with phase field crystal model, it needed some kind of validation, I would say, because there are questions, there are some negative things about phase field crystal model, some of which I explained yesterday. So setting up a polycrystal with a MD, that turned out to be not such an easy thing to do. And in fact, we collaborated with Pinaki on this. In fact, with Lennard-Jones potential, nobody has gotten polycrystals, stable polycrystals with a monodisperse particle. Okay, I'll come to that later. So Pinaki managed to get first polycrystal with some kind of soft potentials, which is very commonly used in to study rheology and so on in soft matter. I mean many soft matter systems. So that I will talk about first, and then so initially we just did that, and then again the referee was not sure that this soft potential is good for comparing with hard solids. Hence we had to do this, and it turned out that there is no good model. I mean, it has not been possible to do it with Lennard-Jones potential. You have to do some bidisperse system, and I'll talk about further analysis. So I'll first talk about these soft solids that we had, soft polycrystal we had. So it was a soft model in the sense that soft disks in 2 dimension, and there's a contact potential. They will interact only if they touch and press against each other. If they don't touch, there is no interaction. Okay, so it's harmonic, you can see, and we worked close to the glass transition because we are looking for a polycrystal. We don't want a we don't want a single crystal. At the same time, we don't want a glass either. So glass transition in these systems occurs at some 0.845. So we worked slightly below that, and in this model there was a viscous term also. So this is an MD. So relative velocities depend. I mean a viscous term proportional to the friction, proportional to the relative velocities of the particles. Okay, so this is the model, and okay, so this is what we got. The color somehow got screwed up, but anyway, okay. So the figure, yes, that is got the X and Y got turned, but that is my fault actually. Yeah, okay, it doesn't matter. So so this is actually the polycrystal for a sheared system, and the shearing directions are the vertical direction. That is, this side is going down, yeah, and that side is going up. Okay, so the walls on this side and that is going down, and on that side it is static. Sorry. Okay, so I should correct. So yesterday we were doing systems where I had velocities put in these two sides. Now we are looking at a system just using the symmetry of the thing. So this side is static and this side is going to the left. Okay. So essentially in yesterday's language we are considering roughly half the system. Okay, so this is the system for our MD. Okay, so what you see, so these are the, so this is the moving wall. So the grain structure that you get here is not exactly similar to what we had there. Few layers here has been kept. I mean, so we basically constructed this layer from some equilibrated simulation and then kept moving those layers at a constant speed in that direction. Okay. So, unlike yesterday, you see that near the wall there are big grains that comes in, which is not exactly same as what we were seeing in the PFC simulation yesterday. So, there is a difference. Okay. And and you see various sizes, and that is the wall at rest, and you do see small grains, some small grains near them also, but basically big and small grains comes almost everywhere. Okay. Now, seeing this structure, you would guess that there will be a problem in detecting a grain, because colors are changing, colors are representative of local orientation. In this picture I am just showing the orientation, I am not showing the defects. Once I show the defects, then you will see it may not be that difficult to recognize a grain. Okay. Okay. So, yeah, so I move to the next system. I will analyze all this together. Yes. No, sorry, rotation of the grain. No, this is just force calculation according to the potential, and they are moving. Yeah, I mean that may cause rotation of the grains, but not the individual particles. Right, individual particles are point particles. They, okay, point particle in the sense that the interaction is based on the center of mass of these particles, and the potential is a contact potential. Okay, so the disks. Yeah.
Have a particle.
Yes, which is a disk.
It has a, you can fix a coordinate system to the axis.
Yes.
To the point.
Okay.
You keep in the simulation, you keep track of how the orientation changes, the XY axis of each particle.
No, no. See, XY axis, there is absolute XY.
Can I make a comment?
Yeah, yeah,
I
yeah.
understand. So, of course, your grains rotate. So, his displacements are tracked.
Yes.
His displacements are
Grains can, yeah.
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 You can do whatever.
Yes.
And as he shared, he will show that the case.
Yeah. But
Grain rotation is automatic.
but grain is a macroscopic emergent thing.
Is isotropic. So,
Yes.
it is the
Disks. The disks don't rotate.
angle. So, it doesn't matter.
Particles, that is.
Do we track it?
Yes.
Do you track it?
No, but it's not possible to have rotation because these are just point forces.
There are no torques on the disks.
There is no torque on each part. See, only if there is friction, which I think Kakarya was talking about. Only if you have friction, then you have the rotation. Otherwise, there is a sense of the particle. Here,
There is no meaning
Each
of
particle, there is no meaning of rotation.
because
The
it's
whole
a
grain can.
Yeah. So the forces are all based on the center of the calculated based on the center of the disk. Okay. Okay, so this is the Lennard-Jones system, and Onuki actually in there are in a series of paper he showed that this you cannot get polycrystals, stable polycrystals with a monodispersed system, but if you put a little bit of very small amount of I mean some impurity particle of different size, then you can. If you mix in too much, then it basically the crystalline nature is I mean the polycrystalline nature is gone, and you get a disordered system. Okay, so we basically adopted this system and used it for our purpose, in the sense that we are interested in the polycrystal part. We need proper grains. Okay, and so this is I am showing actually not the full system. The full system is quite big, about 9,000 particles, and this is just a subset of that. And you can, and I am plotting not just the position of the particles, but the defects also. The defect, the 5-7 defect pairs also you can see, and you can see that there are grains. In the earlier one, with the soft potential, I forgot to mention this information that the number of particles were about 11,000, and the strain rate was of this magnitude. Okay, one important thing I forgot here. Compared to our PFC simulation, here we see few more realistic things, at least one more. That is, you see there are stacking faults, which is a reality, I mean in actual polycrystals, which was not present in our PFC simulation, which you could see here. Although they, I mean, stacking faults do not fall on grain boundaries, because the stacking faults still have coordination number 6. So there are no defects there as such. They do other things, and we do capture them within this soft potential simulation. Okay. So in this case, so this is the grain picture, and so this is the so we tried at various strain rates. So temperature was this, volume fraction was 1, and the very small fraction of impurity particle was added. I did not put any separate color for the impurity particles, but their diameter is, the ratio of their diameters is 1.4. That means the impurity particle is substantially big, and but very small fraction. They come in very small fraction, and typically they go on the grain boundaries. Okay. Yeah. Units are Lennard-Jones units. Yes. Okay. Now it shows difference. So for example, in the PFC model, this was the velocity profile. I would not take that part seriously because that was imposed, that exponential part. So in the bulk of the PFC, this was the velocity profile. And we had two walls. So the velocity profile is actually like this, but in this plot I am showing the only Vy, that is I am showing the velocity along this direction, sorry, Vx as a function of y. Y is the vertical. Okay, so the point is that the velocity goes down into the bulk. Now here also, of course, it goes down, it has to go down because this wall is static, that wall is moving, but the way it goes down is not really same. Here what you see is that very near the wall, this is going into the bulk. Sorry, this is going, so this is the outer plate which is moving, and this is the inner plate which is static. The velocity is going down there. So near the outer plate, you see this, that the velocity is not really, I mean the boundary layer, if you call it, there is no real boundary layer, okay, in the sense that, and this is consistent with the picture that I showed you, that you have very big grains at the boundary, and because these particles are moving almost at the same speed, you can sustain those big grains near the boundary. Okay. So I mean you can see there is a difference in the pattern of movement. Okay, so, and it is not really any point trying to fit any power law or exponential there. I mean you can see the pattern yourself, it's not. Okay, so now I will come to a little more in-depth analysis of about the grains. So first we will talk about grain dynamics, the different things that you see because you apply shear. I mean, see, when you apply shear compared to the case of equilibrium where grains adjust just by diffusion, which is temperature driven, here you are moving the walls, so lots of defects are coming in, so you expect lot of activity here, and you do see enhanced breaking and coalescence. So I will show you all that, and then we will go for the grain size distribution function, both at equilibrium, because at equilibrium it is known that the grain size distribution function follows log normal statistics. Okay, and then we will see how with shear things change and so on. We will also see, so this part I am not going to take up in this talk, it will be part of the next talk. So this is the broad outline. Okay, so now this is actually simulation. Yeah, so what I want you to see is there is a huge grain here, and you see that it will break up into, because of motion of defects, these black things are defects, how it breaks up into 3-4 grains here. Okay. The defects move in a very coordinated way. Again, this is not the full sample, this is just as part of the sample. So what you saw was that how does a big grain basically breaks up in small grains. Now these small portion is not really very close to any boundaries, it is quite in the bulk. You can see 150 to 450 here. The system actually runs from, so this is the PFC simulation, and the system actually runs from 1 to 1024. So this is a 1024 cross 1024 lattice, pretty big. There are about 32,000 particles in the whole system. This is just a part of it, and the point is that these points, I mean this line, your shear is here, meaning this plate is moving in the left. Sorry, I am not showing that upper plate, but it is somewhere far there. The movement is to the left here and to the right here. So this is very much in the bulk. Okay, and you see that I mean defects, many of them together moving in a very coordinated fashion, not necessarily near the wall. I mean near the wall you would expect that because you are shearing, lots of defects come in. Sometimes you have avalanches, but this is not really near the walls. Okay, so this is inside the bulk. So how does breaking phenomena happen? Just because of these defects move in a coordinated fashion. Okay. Now if this was a equilibrium case, you will not see such coordinated movement of defects. In the equilibrium case, small adjustments happen here and there because of diffusion, and grains still change their shape and size in a very, very slow fashion. And
so if we go back to this simulations of Goldenfeld and Dahmen,
yeah.
So what is the difference? I mean, so they're talking about avalanches, etc. So
Yes.
what is the difference in their setup and kind of setup?
Setup is it is basically there. The shearing is in just following their model. So they're just tracking total number of defects, how it is changing in time, and that fluctuates. And sometimes you find that huge number of defects come inside wall. So they did not bother about grains at all. So they were just tracking the total number of defects.
Like we are in the same shear rate regime.
Yes. Yes. Along this direction, yes. 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 I mean the walls are somewhere, I mean the end of the lattice is somewhere there and here. I mean it is 1024, so this is a small portion of that, but this is deep in the bulk. Okay, now now it turns out that this in PFC these grains are much better arranged, in the sense I showed you MD pictures where the defects didn't show so nice arrangements. They are there, but not so nice. Okay, now next one is about grain coalescence. So again, so you can see there is a grain boundary here, and the misorientation is proportional to the, or rather the defect density is proportional to the misorientation. You can see that between this and this there is more misorientation compared to between these two. Okay, so if you have to draw a grain boundary, this will be a small angle grain boundary, small misorientation grain boundary, and that will be slightly larger. These are even larger. So you see defect density is much higher. So what you are going to see in this movie is that these grains are going to coalesce and form a big grain. Again, this is a small subsection.
So under what conditions this happens?
I am shearing the whole system.
Oh, yes.
Yeah.
So you shear this mesh.
Yes. Okay. So and this is, and in the PFC simulation, okay, I should make this general comment, that is in both in the PFC simulation and with soft potential, we find nice non-equilibrium steady state, stable polycrystals. Whereas in the Leonard Jones, as Onuki has also seen, you find long living metastable polycrystalline state, but if you wait for very, very long, everything becomes a single crystal in the Leonard Jones case. Okay, even with impurity.
So for example, in other cases you find critical shear when this starts negative.
Okay, now of course if the okay, now all this happen at some intermediate range, because what happens is if the shear is very small, then you do see such movements, but on a very it happens much sparse. It is almost close to the equilibrium regime where things are happening, but very slowly. If you do it too fast, what happens is that near the wall, the layers start to slide, and in between you find a single crystal. Okay, so this is somewhere intermediate. Yeah.
Does the system ever melts?
Into a liquid? No, it always crystallizes rather.
What factor makes grain coalescence?
Grain coalescence. So it is again the coordinated movements of the defects. Okay, so defects are moving in all possible ways, and sometimes it leads to coalescence, sometimes it leads to breakup. Okay, what I'm saying is all this is happening, all this enhanced activity is happening because of shear. If this was equilibrium, you will not see such big movements.
So it's a kind of probability when it comes with some phase, then only it will get coalescence.
Okay, so essentially when you shear, you inject lot of defects from the moving walls into the system. So if I calculate the dislocation density, for example, this will, I mean, sheared case will have many more defects compared to the equilibrium case. Okay. Okay, so what you see here is that again, you see here a big grain is forming, and this grain boundary rotated also. Initially, I will just do it once more. It was here, and then it is moving, and the grains here, there was another small boundary grain here that has vanished. Okay. So coalescence of grains typically will happen when the grain boundary, I mean the misorientation is low. Okay. But in the process, both the grains have to rotate slightly and come into alignment. I mean, you don't see such things happening here at that large angle grain boundaries, they are somewhat stuck. Okay, so all these extra things are happening. So I mean, grain coalescence and grain breakup. So you expect that if you calculate the grain size distribution, it should be somewhat different. Okay. Now, this is the equilibrium picture. Now, this is a very standard empirical finding from experiments that both in the bulk as well as thin films of various metals, copper, aluminum, they give you a log normal distribution function. Okay, so these dots are from experiment, and they are kind of averaged over various experiments, and so it is taken from a paper by Barmak. In fact, she sent us her original data. So this data she calls a master curve sort of, and so we tried to fit a log normal through that, and we find that it is not a very good fit, although experimentally it is kind of accepted as a, I mean, all metals follow log normal distribution at equilibrium, but they never plot log. Okay, they will always plot exponential. Rather they will always plot the normal plot in which this tail cannot be resolved very well. This will be all here. Okay. So what they will see is something going up and then coming down very drastically, and they fit log normal, which is a good fit for them. But you can see that it is not a very good fit. I mean, at the tail there is deviation. Now, we first wanted to validate our simulation, our PFC simulation, to get this. Okay, because PFC has problems. So now, so this is our equilibrium simulation, and you can see these two curves are almost parallel, but we don't have points here. I will come to that. Now, in order to plot such a graph, you have to first find out, I mean, you have to detect grains and then calculate grain size and make the statistics. Okay. Now, detecting grain is not a very easy thing, which I will come to at the end. In the sense, typically when your grain sizes become very small, definition of grains become ambiguous. Okay. Now, there are various methods of doing that. So, in our simulation, so in the experiment it is not so difficult, because so you see there that the x axis is normalized with the average area. So, in the experiment, when they talk about small grains, I mean, in these experiments, it is almost 85 I mean of the order of 100 micron. A small grain is roughly 100 micron, and that will have many particles. In our simulation, in this regime, we have about 30 particles. Okay. So, we cannot detect small grains reliably. So, we do not have reliable data for this portion of the graph, which is about small grains. Okay. So, we take this as the validation, and there was another big simulation, again a phase field simulation by another group who claimed that they have verified this log normal quite well, and in fact they have small grains also. But we had so we talked to them and we found that they have ambiguities too, but somehow they say that because their data is matching with the curve, so that they take as, so this is a group in Dresden by, and the person is Voigt, Alex Voigt. Okay. So, so what we get is, at least for these scales, it is almost parallel to that. Whether it is log normal or not, that is a different question. So, this is sort of a validation for our PFC code. Okay. Okay. Now, so now we go for the non-equilibrium case, that is the sheared case. Okay. So, in the sheared case, so this is the main graph of this paper actually, it got published recently. This is a rapid com of a new journal, Physical Review Materials. I mean, we fought a long time for with PRL, and then it was not convincing to them anyway. So and they suggested about this journal which has just come out recently. Okay, so here what I show is the equilibrium data. The blue thing is our, and this is the graph, I mean the experimental one which I showed, and the scales, the y axis is somewhat shifted between this graph and this graph. On the x axis I have normalized by average area. Okay, here also actually our data was almost on top of this, but just to show the show that it is reasonably close, we have shifted the y scale slightly for our data compared to the experimental data, but it was basically falling here. Okay. Now, this is the all the non-equilibrium data we had across various simulations. So, we have PFC at 2 different strain rates, 10 times different. Then we have this MD with this Lennard-Jones comparable strain rate, and then we have the soft solid, so all comparable strain rates. Now, at slower strain rate, things become very, very slow. So, getting data becomes a problem. I mean, you have to really do a very long simulation. What we did was that we did many initial conditions, because things evolve very, very slowly at small strain rates. So, getting this equilibrium, for getting this equilibrium data, we did not go for this 1024 square system. We did it for 512 square, and that too took us and about 50 initial conditions to generate this equilibrium data, because things are very, very slow. Comparatively, the non-equilibrium is faster because you have the shear. So, you can see that okay, the tail is quite noisy, and so we fitted this to a modified log normal. Okay. And again, we do not have data in this regime. Now, a modified log normal of this kind would dictate that the peak will come at smaller grain size. Okay. So, if we take this as a reasonable fit to this data across these various simulations, so there, first of all, there is some amount of universality across models. We do not have a big range of shear rates, and so and we also do not have, we cannot go to that regime of small grains. So, the only modification in this modified log normal is that factor alpha. If this was just a log normal, you will have alpha equal to 0. Okay. And in this fit, we gave less weightage to these points because you are going into that small grain regime here. So, alpha is just 0.2. Okay. So, hardly much modification, very, very small modification. Okay, so this is of course a surprise, because even with all that heightened activity of grain coalescence breaking and all that, the distribution doesn't change much. Okay, so this is our main result. Now,
Don't you have experimental data or nothing?
for shared case, no, there is none. Yeah. So it is basically asking for that.
Actually, for metallic systems, it will be very difficult to do simple shape. You can only do extension.
I see. For colloids, it might be possible. Yeah, yeah. So colloids, I've talked to people who work on these colloidal crystals. They would like us to change to constant shear rather than constant strain rate. What we have is a constant strain rate. We are moving the walls with constant speed. Okay. So then they can, at constant shear, they can look at.
In the PFC formulation, can you do a constant stress?
It's not easy to do. Yeah. Because I mean, you saw that in order to, in order to simulate shear, we had to move the particles. So PFC works in terms of the particle density. Okay, so putting a force is difficult there. I mean, yeah. Okay, so now I come to a little bit of analysis that so based on this grain breakup and grain coalescence, I mean, I showed you movies. You see that more of them happen when you have shear. Okay, so you can think, I mean, you can interpret this small change in the following way. So I'm thinking in a stochastic terms now. So let's say, so I concentrate on grain area as my variable. So I mean, so grains are, I mean, the distribution function is in terms of area. So due to this dynamics, how do the areas change? We see that when, let's say you have a probability of a particular grain size. Okay. Now when this grain breakup happens, what you are doing is that you are shifting probability from larger grain size to smaller grain size. So in the area space, there is a probability current from large grain size to small grain size when you have a breakup like this, and this is the opposite of that. So weightage is shifting from small grain size to large grain size. Okay, so you can think of this in terms of a stochastic equation, a Fokker-Planck kind of description. Now people have done this before, but yet this formalism, I mean, it does not lead you to log normal statistics even for equilibrium grains. Okay. So there is no theory actually which can show you rigorously that either derive or even numerically solve a equation and show you that how you get log normals. Okay. Now, so again, this is not really a first principle theory. We are just trying to interpret that. Let's say you are having breakup phenomena and you are having coalescence phenomena. We can at most comment that which one is stronger with shear. Okay, using this picture. So one of the famous, I mean, theoretical laws, I would say, in this grain size physics is Mullens law. Now he showed that, so this is for again equilibrium case. I mean, in the equilibrium, how just so in the equilibrium, grains adjust their shape by diffusion of atoms, and he formulated this problem in terms of the curvature of grains. Okay, so in his formalism, so he has polygons, the grains are polygons to him, and then he came up with this law that the grain area will increase if the number of sides is more than 6. Okay. So for example, a triangular grain, I mean a grain which looks like a triangle, will eventually die out because its area will shrink. On the other hand, if the polygon is more than 6, then it will grow. But you can see that this is not in terms of area, this is in terms of the sides of the triangle. So this law really doesn't actually help us to understand the statistics of grain size. Okay. So you can think of a equation like this. So, this is the probability that a particular grain size has certain probability P of A at a given time. Now, this is the flux in the area space, grain area space, and this flux you can imagine that so there is a drift term in the flux and there is a diffusion term. Now, if this was equilibrium, you will not have this drift term. Yeah, okay. I would take back that statement. Yeah. So, if this formalism have to give you a log normal kind of thing, you will see that, okay, first of all, you cannot rigorously get a log normal from here. So, okay, so curvature of the grain is the driving force in this formalism, even at equilibrium. It happens via diffusion. So, atoms are diffusing and they diffuse in a manner such that they can lower the curvature, they can make the grain boundaries flat, that is the driving force. Okay. So, microscopically it is particle movement driven by KBT, but macroscopically it is the curvature of the grains that is getting adjusted. Okay, because grain boundaries have a high energy and so on. So, the grain breakup in this language would mean that, so grain breakup would means that you from big grains you are forming small grains. So, there is a probability current in the area space towards small grains. Okay. So, this current will be negative in that case, and grain coalescence you are forming big grains would mean that the flux will be positive. Now, the distribution that you have, it has a peak somewhere middle. I mean, let us say some log normal or some other case, it goes up and it goes down. So, there is a peak. Now, in order to form this peak, you need flows from both sides. I mean, both small grains has to go towards bigger grains towards the peak. I mean, this function P of A has a peak at some finite area. So, smaller grains has to go to that size and bigger grains has to break up into that size. That is why you will get a peak there. Okay. So, now, yeah, and of course, this I think stochastic picture is okay, because after all this is, I mean, this is a very random phenomena happening. So, stochastic picture could be okay, but one needs to formulate this in a way so that you can, instead of writing down this kind of terms in an ad hoc manner, there should be some way, which is of course not easy, to come up with how should the drift term look like. Okay. Now, if you take the drift term like this, okay, so this, I mean, it cannot be derived. If the drift term is like this, then you can show that this will lead to a log normal distribution for that probability. Okay. So, what we are interpreting it as is that, so what we found is that the drift term changes in our case by that amount alpha, and this will lead to that modified log normal distribution. Okay. And you can see that since alpha is positive, your drift is becoming more negative. Okay. So, this drift comes on the right hand side of your flux here, this J. So, this is becoming more negative. That just means that you have dominance of breakage than coalescence. Okay. So, this is just a interpretation, this is not any. So, all that we can say is that yes, there is a extra breaking events happening and extra coalescence happening, but on the net coalescence is dominating, and that is why your peak of your probability is shifting towards smaller grains. Okay. I mean, this you could kind of, I mean, this conclusion you could see even by looking at the peak of the P of A, which I plotted, which just showed the peak has shifted to smaller grain size. Okay. So, this does not really tell you much. Okay. Okay. So, now in the, how much time do I have? 20 minutes. Okay. I am almost done actually. Then we can, yeah, move on to the next topic also. Yeah, fine. Okay. So, about grain, I told you there is a problem about detecting small grains, I mean any grains actually. So, there are, so this method turns out to be quite popular, forwarded by Singer in 2006. So, they use some wavelet based method, and there is another method which we actually used, and there is a reference for that too. Both have limitations. So for example, this method doesn't work if you have small angle grain boundaries. Okay, I mean, of course, there are small angle grain boundaries, but this method is very inefficient there. So two grains which have a small angle grain boundary, which will look like a single grain in this method. Okay. Sorry? I'm coming to that. Okay, so I see. So what it does is that in this method, first you have to transform. I don't have much details here actually in this. So first you have to transform your you have to transform to a density picture, a continuous picture first of all. Okay, so if you are doing an MD simulation, you have to interpolate and go to a density picture first, and then you do certain wavelet transformation with some particular basis, which I mean it is there in this paper, and there are various versions of it. If you do that, what you produce is a graph, a picture like this. So this is one of our PFC configuration. So in the PFC you directly have the density field. So after that transform, it looks something like this. So it has few discrete colors. Now from here you can see that it won't be still very easy to detect grains. Okay, I mean the yellow ones look prominent, there are black ones, but there are lot of regions where it is very difficult to, for example here, it is very difficult to detect grains. Okay, meaning the two yellows are separated by a small thin red region. So, whereas you can have red grains somewhere else also. So we found it quite difficult, and so we did transform from that picture to a grain picture, and it looks like this. And you can see that there are lots of regions which are very, very ambiguous. You have this thick grain boundary like walls, and you have some clear cut grains. So and there is a proliferation of small grains, and I think this is the artifact of this method. We tried to improve it in all possible ways, it didn't really give us much better. So we found this method, the second one, to be more reliable, which is wherever you see partial grain boundaries, just connect them. Okay. So for example, again this method is okay when you have when you have big misorientation, you have many of them, so you just connect this in between points by these lines and you try to form your grains. But when you have small angle grain boundary as well as small grains, so for example, if you think of this region, there could be, there are many defects, and there could be more than one ways to connect defects. Okay, and this problem typically happens at small grains. Small angle grain boundaries are not such a problem. For example, I will show you. So for example, if you look at this boundary, there are not too many defects, but distance between the defects is somewhat large, but still so this is basically a search based method, that once you find a defect, you try to look for defects in your neighborhood, and you increase your range of search, and you try to connect lines. Okay, and this eventually leads to this kind of picture. Again, you can see this has problems. You can see there are often, for example, orientation here in this color picture is changing to some extent. Say for example, this stands for a orientation which is a small orientation, with respect to some axis, whereas you see change of color, but you don't see defects. Okay, so this still gets counted as one grain. Okay, so such problems are there. Okay, so we tried. Okay, so once you get this kind of grains, then you need a algorithm for counting how many particles are there within that grain. So that we had done, that is not a problem. So all the data that I have showed you is based on this method of detecting grains. Okay, and here it is not very reliable for small grains, but it is better for bigger grains. Okay. And we found that the other group, which claimed to have a very nice log normal fit and so on, they also have these problems. Okay, so that's a summary. We have shown that that the distribution is still very close to log normal despite of all this enhanced activity in terms of grain breakage, coalescence and so on, and a limited conclusion that the breakage seems to be slightly stronger compared to coalescence. That makes and that's what makes the peak shift slightly only, not too much. Okay, so this is end of this, and so I have still 10 minutes or something. Okay, fine. So maybe let me get started on the next, which was supposed to be the part 3. It doesn't matter. Okay, so this is with
one question. So you have also looked at the equilibrium precization.
yes.
In equilibrium, are you sure that there will be a polycrystal, or is it both the two things can happen? And just because of entropy, a polycrystal may be stabilized, or it can be that it is taking enormous amount of time.
Yes, that is certainly the second one is the case for Lennard-Jones bidisperse system, of course. But for soft and in the PFC case, we had stable non-equilibrium polycrystals.
So Lennard-Jones bidisperse Lennard-Jones, you are saying that it is
Eventually, yes, a very long time to form a single crystal.
Actually, for the one component soft particles, we are at 0 temperature. So we have generated those structures, but if you have finite temperatures, it will eventually go to a single crystal.
Yeah. So
The interesting thing is under shear, even this one component system still remains polycrystal.
sorry, what did you say?
I'm saying for the one component system under shear, it still remains a polycrystal, whereas for the binary mixture, there is a
Okay,
tendency
yeah,
to form a single
right.
But as soon as you put under shear, then it becomes non-equilibrium.
Yes.
For other processes.
Yes.
But in principle, and many of the studies see that if you shear, they are going towards the ground state more often.
Yeah.
But it's not guaranteed.
So this is a study with again with polycrystal, but now driven by a body force. Not a surface force like a shear. So body force could be, let's say, pressure. Let's say, think of a flow under a constant pressure gradient, or it could be under gravity. Now there is a difference between pressure and gravity. The gravity is a genuine body force in the sense, okay, that I will kind of show you. The plan here is that so how to implement the body force within a PFC and a MD and stability of the polycrystal. I will show some displacement pattern and fluctuations. Okay, so first within MD it's quite easy because you are dealing with particles and you have a force. When you have gravity, you just have a force mg. So basically it's a constant force applied on all particles. Okay. Whereas in the continuum language, if you which get used in PFC, you have to think of the momentum equation. So gi is the momentum, rho is that, so phi is the density, this is the velocity. So in the momentum equation, which is the Navier-Stokes equation, let's say, the body force come as g into the density. This is a constant. Okay. So then the way you get your final equation, the working equation, that's a density equation, which is basically you have to combine, which I showed yesterday, which you have to combine the momentum equation and the continuity equation plus incompressibility, everything together. That will just lead to an extra term like this. If you remember, in the sheared case, this term was very similar, except that instead of g, you have the velocity of this, in the imposed velocity, and the velocity was a function of y, which was falling off exponentially into the bulk. Okay. So here it is simpler, it is just a constant. Okay. So it's just everything almost is same. Instead of a space dependent velocity imposed gradient, you just have a constant acceleration, that's all. Okay. But because of this, so what you can imagine now is that, so all the particles are being pushed at by some gravity force. Now, why I said pressure is not exactly in this category, slight difference, although people have actually mimicked pressure also by a term, putting a term as just a constant into some kind of gradient force, but I will not try to do that. So, I mean, why this difference between pressure and gravity is the following. So, if you look at this momentum equation, in case of fluids, the pressure terms comes as minus gradient of P in the momentum equation. Okay. Now, so if you even can generate a flow where the pressure gradient is constant everywhere in space, suppose. I mean, in experiment that does not happen. Experiment, what you do is you apply a high pressure on one end, a low pressure on the other end, and then the thing flows under a pressure gradient. It is not guaranteed that the pressure gradient will be constant everywhere. If it is a simple non-Newtonian fluid, that can be achieved quite easily. Otherwise, pressure gradient may also be a local quantity. Now, so in this equation, gravity will always come as g into density, but pressure will, if you can at all create a case of constant pressure gradient, then this is just a constant in this equation. Okay. Now, you can think in the following way, that after all this density field, I mean, so putting a constant here versus putting a constant into density is not so bad for polycrystal for the PFC, for the following reason, because in the PFC language you have a density, but this density is non-zero only at the particles. Okay. So, this is almost like series of peaks in space. So, putting even for pressure, if I say this will mimic my effect of pressure, it is not so bad, because it is a constant multiplied by a field which is operating, which is non-zero only at the particle positions. Okay. So, on wherever there is a particle, you have a constant force. Okay. So, your density is not real, I mean, wherever the particle is there, your density is 1, otherwise it is 0. Okay. So, in that sense, you could think of putting the effect of pressure by this kind of density dependent term. Okay. This is provided you can make a case where the pressure gradient will be constant everywhere, which is not real, I mean, that really does not happen in a complicated fluid. Okay. So, we will just go ahead with this. So, the clean case is flows under gravity, and in the MD it is just a extra constant force on all the particles, which is foolproof. Okay.
Sheared comes from the walls.
Okay. Now, yeah. Now, in this case, in the pressure driven case, or let us say the gravity driven case, we did not mix shear with this. We just kept the wall static and just pushed the fluid by gravity or pressure. Okay. So, yes. So, because there will be no slip type of condition at the wall, and the whole thing still has to move because of the force, there will be lot of gradient near the wall. Okay. So, for example, if this was a simple fluid, you would expect, so here I am showing so in our PFC simulation for the polycrystal, I am showing the velocity versus y. If this was just a liquid, then you will have a parabolic profile, a simple liquid. At the walls it will be 0, and then it will be parabolic. Here what happens is that first of all I have to put a rough surface which basically ends here and there. Now, we have varied the roughness in some way, although we did not see too much of difference in the evolving V field. Now, so I won't go into the details of how we created roughness and so on within PFC. So we have done the MD for this also. So in the MD, a preformed polycrystal was taken, and that has been put here on the two sides, and because it was polycrystal, it was not a smooth surface. Okay. So what we find here is that irrespective of the amount of force, the flow, see the flow is very, very slow. things are moving but flow is slow, things become a plug-like eventually at long times. But initial times the flow slowly evolves from a nearly parabolic profile to a plug-like flow as time evolves. Okay. So, we have plotted them in a way so that the fronts so that the fronts can be seen at the same place. But what actually happened in the simulation is that so first of all, this is a transient phenomena, that when you start the simulation things starts to move in a slow fashion, but eventually once you have the plug flow this whole system keeps on moving forward, and the grain structure that you see in the bulk do not change too much. Okay. So, right. So, we have plotted in a way so that we can show the fronts in the same plot. So, with time the velocity of the bulk region actually increases and becomes stable after sufficient time when you have full plug flow. Okay. So, you see that some kind of shape evolution is there of the front, so that we quantify in some way. So, the way we do that is that we fit so we look at the curvature at the front of the flow. Okay. So, we fit a parabolic profile to the portion which is curved. So, how do we the way we choose the portion is that wherever the derivative of the velocity changes too much, we stop there and we take that much portion and fit a parabola to that, and the curvature of that we calculate. Okay. So, with time the front is becoming flat, so the curvature with time becomes very, very small, and these are some arbitrary units. And so, initially the curvature is quite high, that purple line, and with time it decays. And if you give more force, this 20 times force between these two symbols, if you give a higher force it will become more and more flat, and I think so at low force you can manage a high curvature in the initial time, but at a high force even at that initial time your curvature is low. So, this is showing that the curvature even the front becomes flat and you get a flat flow. Okay. So, we do the same exercise for MD also, and there, so this is a comparison between PFC and MD of the, again these are Lennard-Jones bidisperse. So, here also you find that with higher force, or let us say higher gravity in our language, you find a slower decay, and so PFC is cleaner, this is a little more noisy, but the features are roughly same. We did not try to fit anything to this. Okay. Okay. Now, I think so this is slightly change of track, displacement of the particle. So, what you just saw was the velocity. Now, here is the displacement of the particles. Now, so this is for PFC, this is for MD. Now, here, so you saw the displacement profile is sort of going from parabolic to plug. So, which means that eventually most of the particles are moving at the same speed, okay, displacement wise also. So, they will be displaced equally. Okay. So, that gives rise to this peak, and with time, so the purple one is lesser time, this is higher time, later time. So, with time the speed is increasing. So, more and more particle, I mean it is becoming more and more plug. So, more and more the peak height goes up with time, and so both has peak, but the structure around the peak here is not the same in this. So, this is the PFC for a Lennard-Jones, and bidisperse Lennard-Jones. Now, we did similar kind of analysis as I showed you for the other shared case, and we could come up with some profile for this portion, this rise. So I didn't put that formula here because I had plans of giving this presentation in the third talk. Anyway, and we also looked at the fluctuations, and the fluctuation is highly non-Gaussian. By fluctuation I mean we subtracted the mean. So here what you are seeing is delta Vx, that means the forward velocity is by far much more dominant than any transverse speed. So for every particle we basically subtracted the mean. So this is a fluctuation, and in both PFC and MD there is a non-Gaussian tail. Of course it's more pronounced here than here, and it's much smoother in the case of MD. By the way, you still have grains, but quite large grains in the bulk, and they are kind of flowing forward. Okay, so I think that's the last graph I wanted to show in this context for the pressure driven case. So I will stop here. Yeah. Yeah.
So let's go for lunch.
Okay.
Very good. And last topic, you can start from here.
Yeah. Actually.